Okay, so hi everyone. So welcome to the PowerPoint portion, the lecture portion. And so our goals and understanding the Prius and hybrids in general are, well, one, we want to say what is the environmental impact? Does this increased MPG, this reduced fuel consumption, does this really translate into a meaningful environmental impact? Basically, the short answer is yes. And that's what the focus of this video is going to be on. And then the second video will be how does the hybrid drivetrain actually give you such good MPG? So how do you get such good performance? And then finally, we're going to say, okay, so once we understand all the reasons that the hybrid drivetrain works and gives you this good performance, how can you optimize that performance? In other words, how can you win the Prius video game? So let's dive right into environmental impact here. So one, we have to say, well, how are we going to measure that impact? Are we talking about oil consumption? Are we talking about energy, materials, other things? These are all perfectly good ones to talk about, and particularly oil, or oil and the derivatives. And then the other one that we think about a lot, especially with hybrids and other light-duty transportation, is global warming potential. How much does this contribute to global warming? And because this is a summation essentially of CO2, carbon dioxide, but also other greenhouse gases. We can think of those. We can take these other greenhouse gases, and I will talk about this in a separate video, but how we actually do this, but we can subsume these into a metric called CO2 equivalence, or CO2e. And this is nice as a metric because we can look across the entire life cycle of the vehicle, where fuel comes from, when it's combusted in the engine and the CO2 is released from the tailpipe, and also the vehicle manufacturer, et cetera, so-called vehicle cycle. And CO2 out of all of these gases can be by far the dominant one, and CO2 coming out of the tailpipe is the dominant component. And so as I just said, we're going to choose this CO2 equivalence as one of our primary metrics, and our other primary metric being gasoline consumption. Now we'll focus on gasoline vehicles because that's the vast majority of light-duty vehicles in the US and all production hybrids in the US. And again, but by looking at these CO2 equivalents, it's easy to look at these other life cycle impacts beyond the tailpipe. And so, okay, so what are these life cycle impacts that we're going to look in the context of CO2? Well, again, we divide this into the fuel cycle, and this is about 80 to 90% of life cycle emissions for both hybrids and for conventional vehicles. And then for the vehicle cycle, which is the procurement of raw materials, assembly, and then just maintenance end of life phase as well for the vehicle. So all that, and that's about 10 to 20%. It's a little bit more percentage-wise for hybrids, and a little bit but it's still only about 10 to 20%. The dominant component is this fuel cycle. And the numbers that I'm going to give you here are going to be largely based on Argonne National Labs GREET model. And so there are two versions or series of this model. There's GREET 1, which looks at the fuel cycle, or what we can think of as the fuel cycle, and then we're going to divide that into all that energy that comes from extracting the fuel, refining the fuel, distributing it. That's the well to pump component. Then burning it here, the pump to wheels, and then this vehicle cycle again, as I just said. And so that's how it's visualized. This comes from the Argonne National Lab GREET publication, and so that's where these numbers are coming from. I'm not just making them up. So looking at this fuel cycle, well, again, we're talking about well to pump, so not to belabor the point, but so the well to pump, again, for typical crude oil is about 20% of the life cycle greenhouse gas emissions, and about 10% of the life cycle greenhouse gas emissions are the energy to extract oil, and about 10% for the refining stage. Transportation, distribution, these other things are relatively minor components for most crudes. And so as we talk about well extraction, that's our first step here. And that's, for conventional oil, that means drilling for oil and pumping it out. On the right here, this is an image, an aerial image. You can see all these just different drilling platforms here that are fragmenting the landscape. These could be both conventional drilling, or these could be fracked wells as well. And in a separate video, I'll talk about how fracking is performed and how that differs from conventional oil, and how shale or tight oils come from that. So by the way, fracking is the dominant source of oil now in the US oil production, not globally. Globally, it's still conventional oil by far. But natural gas and oil are produced by similar geologic processes, and they're both extracted by similar technologies. And one of those technologies is hydrofracturing or fracking. There's also other unconventional oils like the tar sands, heavy tar sands oil. And so this is an image of the Alberta tar sands. And these are extracted through kind of open pit mining and also other in situ techniques. And I can talk about those in separate videos as well. But all this takes a lot of energy, and unconventional oils and tar sands especially, they take more energy than conventional crudes to extract. But even for them, the overall contribution to the life cycle is less than just burning it in the tailpipe, at least in terms of the CO2 emissions. These tar sands, in particular, the Alberta tar sands, are what are at the center of the Keystone XL controversy as well. And now at the refining stage, well, this is just, again, a refinery. There's all kinds of stock photos of refineries. And refining takes a significant amount of energy too. We lose a significant amount of energy at that stage. And the essence of refining, so you're taking crude oil and you're turning it into different oil fractions, refining it there. And the essence is basically distillation. And so we can think of this as you're just distilling this oil into different fractions. And so you take oil, you heat it up, and then you distill it just like you would with alcohol or whatever. And so the heavy fractions like asphalt and really heavy fuel oil, those come out toward the bottom. The lighter fractions, which are fewer carbon, shorter hydrocarbon change, like propane, liquid propane gas, liquid petroleum gas, gasoline and other things are here toward the top. So gasoline's a relatively light fraction. And then, you have diesel here, which is a heavy fraction. So gasoline is a refined crude oil product. And gasoline is obviously by far the dominant fuel in the US, although diesel is widely used in heavy transport, and there are also diesel trucks and things like that. Okay, so then in our fuel cycle, so that's our well to pump emissions, again, mainly from extracting, varying with the crudes, and then refining, separating this into these different fractions, and we're mainly going to be thinking with gasoline. Tailpipe, well, that's here. Well, the tailpipe is just, and this is 80% of those life cycle greenhouse gas emissions, just taking that fuel, burning it, and you get CO2 and water. You add oxygen, you get CO2 and water. And that's pretty much, that's the vast majority of the CO2. And if we actually look at some numbers, we can divide this up and we can put some numbers to this. So what we're going to say is per gallon, say for gasoline, and we're going to use, so we're going to mix imperial US units and metric units here a little bit, because we're just going to use what's most commonly used. And we're going to use as our metric kilograms of CO2 equivalent. And what we're going to say is that the tailpipe for gasoline, well, it's just under 9 kilograms of CO2 equivalent per gallon. And then you add about 2 kilograms of CO2 in these upstream well-to-pump processes here. So you get around 11 kilograms of CO2 per gallon. That's for gasoline. For diesel, which is this heavier fraction, it's more energy dense on a volume basis. It's heavier, so it's denser. You pack more diesel into a gallon of diesel, pack more hydrocarbon chains, right? And so because there's just more hydrocarbons in that gallon, you have more energy, but you also have more CO2. So the emissions for a gallon of diesel are a little bit higher, about 10, 11% higher than for gasoline. And so if you're comparing diesel engines to gasoline engines, that's one of the reasons they get higher MPGs. Diesel engines do have intrinsic advantages over gasoline engines that give them higher efficiency, but one of the reasons you get higher kind of sticker MPG is just this fact that they have more energy in the fuel. And so you should adjust down by about 10% if you really want to get more apples to apples comparison of a gasoline engine and a diesel engine. So a 30 mile per gallon diesel, it's really more like a 27 mile per gallon gasoline. And we can just think of this in kind of a rule of thumb. If you're thinking of this, 1 gallon of gasoline, that's about 10 kilograms CO2, nice round number. So if you said 500 gallons of gasoline, which is about what a typical driver uses in a year, maybe a little bit more, well, that's about 5,000 kilograms, which is about 5 metric tons of CO2 equivalent. And so for comparison, really a little more, 5.5 if we're using 11. And if people are using a little bit more than 500, we're getting more closer to 6 metric tons of CO2. But for comparison, so per capita, the US generates a little under 20 metric tons of CO2 per person per year. Globally, that number is around 7 metric tons of CO2 per person per year. So a typical driver in the US is already generating close to or around the total yearly emissions from everything of the average global citizen. So this is like a pretty, this is a non-trivial amount of CO2, to put that in some context. All right, great. So That's gasoline. That's these different fractions. That's how much CO2 they emit at the tailpipe when you burn. So let's relate this MPG, because this is kind of our primary metric here, to gasoline and the CO2. And again, so now a typical car in the US in the fleet, because they're older cars, is around 22 miles per gallon. Average new car is just about 25 miles per gallon, or average new vehicle, or including cars, SUVs, trucks, all averaged together. That's based on EPA numbers. And so, but there's a huge range, right? You have like the Prius Eco-Trim gets an EPA estimated 56 miles per gallon combined. Whereas there are plenty of new trucks and SUVs still that still get less than 15 miles per gallon. So there's a huge range. There's a fourfold range of production vehicles that you can buy today. And so we need to understand how this MPG really relates. And there's a simple but somewhat subtle, or just something you don't think of, relationship between MPG and fuel consumption, because we're really interested in fuel consumption and the CO2 emissions and other harms associated with that. And so there's this what's called a hyperbolic relationship, and you'll see what that is graphically in just half a second. But just for a second, let's suppose you had a vehicle that was getting 10 miles per gallon and you went 100 miles. Well, 100 divided by 10, that's 10. So it would take you 10 gallons of fuel, right? Now, if you went to 20 miles per gallon, that same 100 miles would only take you 5 gallons of gasoline, 5 gallons of fuel. So you save 5 gallons by going from 10 to 20. Now, if you go from 20 to 30, it's the same arithmetic increment, right? Added 10 miles per gallon. Well, now it only takes you 3.33, repeating, but we're rounding, gallons of gasoline. And so now you've only saved, a little over a gallon and a half. So your savings were much bigger going here from 10 to 20 than 20 to 30. Same thing, as you go from 30 to 40, well, you save less than a gallon now. You go from taking 3.3 gallons to 2.5 gallons. As you go from 40 to 50, you only saved half a gallon, right? So you see there's this law of diminishing returns. The same increment in MPG gives you a much lower fuel savings. So, it's really important to focus, really think about reducing fuel consumption down here at this lower MPG range. And we can look at this graphically. So again, this curve here is what's called a hyperbolic curve. It's saying, relating our MPG to the number of gallons of gasoline it takes to go 100 miles. And so our fleet average, well, it takes around 4.5 gallons, and our average new vehicle is around 4, around 25 miles per gallon. It's about 4. I think I used 24.9, which is the average in 2017 or 2018 for this figure. But it's about 4 gallons per 100 miles. And so as you move your MPG around, by what might be, just might not seem very much, plus or minus 5 miles per gallon here, you're getting very large changes in the amount of fuel you're actually consuming. As you go up here to like our best new car, which is, just under 60 miles per gallon, we're doing much, much better, right? We're only using, we're using less than a half, or even almost down to a third of like a fleet average vehicle. But if you went, if you magically increased your MPG to 100 miles per gallon, your savings here are very minimal. They're not nothing, but they're minimal compared to your savings here. So this is an important thing to understand, that the same change in MPG means a lot more at the lower range than it does at the higher range. Going from 40 to 50 isn't as nearly as big, remotely as big a deal as going from 10 to 20. Same thing here, these differences are not as important, and we want to get our cars kind of up into this range here, and then they're all somewhat similar. And now if we just convert this to emissions, and now I'm going to say as yearly emissions, CO2 equivalent emissions, well, I'm going to assume 12,500 miles for a typical car. That's just about what it is based on transportation surveys, highway data, etc. That's for a typical driver. A typical car is just a little bit less because there's slightly more drivers than there are cars. Sorry, the other way around, slightly fewer drivers than there are cars. In any case, if we just multiply, the CO2 equivalent per gallon of gasoline, now we're going to say that, our worst new vehicles are getting over 10 tons, metric tons, this TONNES, that just means metric ton, over 10 tons of CO2 per year. Our average is around 6, 5 to 6 for a new fleet average. And then our best vehicles, our best hybrid vehicles are getting somewhere in the neighborhood of a little over 2 metric tons of CO2. So, 5-fold difference really almost between the worst new and the best new vehicles you can buy still on the market. So quite significant. And so then just to finally reiterate, again, our implication, if you went just from 10 miles per gallon to 11 miles per gallon, well, to go 100 miles at 10 uh, miles per gallon, it takes you 10 gallons, sorry. As you go to 11 miles per gallon, it takes you 9.09. So you saved almost a gallon of fuel. Well, if you went from 50 to 100 miles per gallon, you go from 2 gallons per 100 miles to 1 gallon per 100 miles. So, and there you save exactly 1 gallon, but these are almost the same. These are almost the same in terms of absolute fuel and absolute CO2 savings. So vastly more fuel savings potential at lower end of efficiency. It's really just important to keep in mind. Now, all right, so I've said that, at this low end efficiency around 10 miles per gallon, this is just abysmal CO2 emissions. It's 5 times as much CO2 as a hybrid, typical hybrid. So let's compare the Hummer H2, the infamous Hummer H2. This is an ad from them saying neat is a very subjective word. The Hummer like nothing else. I agree, there really is. But in any case, so based on just MPG, Priuses and other hybrids, comparable hybrids, use vastly less fuel, vastly less resources. And yet there's this idea that hybrids are just as bad or even worse than the Hummer. And this idea of comparing it directly to a Hummer comes from the so-called dust-to-dust report by this marketing research group. This was back from 2007. And this is just kind of a zombie statistic at this point, or zombie idea that's entered the public consciousness to some degree. They claimed that the energy cost of a new H2 was greater than the energy cost of a new Prius. And there have been many, many refutations of this report. It's almost absurd. We're not going to spend any real detail on their claims. We are going to look at using numbers from like Argonne National Laboratory GREET model so that we're actually going to do this comparison. But this idea is out there that somehow the energy involved in producing the Prius or other hybrids is so great that it makes it even worse than kind of the famous Hummer. And now let's just compare these guys. So in one corner here, we have our Hummer weighing in at around, depending on the model year, 6,400 to 6,600 pounds. And it's so heavy that at the time it didn't have to get an official EPA MPG rating, but there was at least one Edmunds test that clocked in at 9.2 MPG. And there's a few other published ones that are all 9 to 10 miles per gallon. So it's right there, that 10 mile per gallon. It's over 3 tons of vehicle. In our other corner, well, let's look at the 2005 version, since if we're kind of relating this to the dust-to-dust report, this was back 2007. So let's look at, Hummers were produced in the mid-2000s. So let's look at the older edition of the Prius, just to be careful. So 2005 Prius got 46 mpg according to the EPA. So a little, not as good as the new ones, but still pretty good. And its curb weight was a little under 3,000 pounds, about 2,900 pounds. So if we just do the basic math, we just divide, MPG and assume we went 12,500 miles a year. Our Hummer here is over 1,300 gallons. The Prius here is under 300. Pretty big difference. Over say 160,000 mile lifetime vehicle life, this is just being assumed, but it's a reasonable assumption. We're looking at over 17,000 gallons versus 3,500 gallons for these two different vehicles. So really, if you're claiming that the Prius uses more energy, you're claiming that it takes the equivalent of 14,000 gallons of gasoline extra to produce the hybrid battery here. Now, the hybrid battery in a Prius is about 1.3 kilowatt hours. That's its energy storage, and that's equivalent to a few 10 pounds, maybe 100 pounds if we're including everything. So you're saying that 100 pounds of battery pack, et cetera, here outweighs this, not only this extra well over 3,000 pounds of vehicle production, but also this 14,000 gallons of fuel use over the life of the vehicle. It approaches absurdity, this claim. And in fact, it is absurd, but let's just look at this. So let's look at this vehicle cycle here again. So again, we're just gonna go to the GREET 2 model from Argonne National Lab. We're just gonna quote them. And basically what their results, and there are other analyses, EPA has done analyses, there are other analyses too, but they all basically agree that overall, this vehicle cycle is dominated by the materials production. So that's mainly the iron and steel, the aluminum, and then the other plastics, et cetera. And then the vehicle assembly. And so these two things are each about 50% of the overall impact in terms of vehicle cycle. And both of these impacts scale linearly with vehicle weight. In other words, if you double vehicle weight, you double the impact, roughly speaking. Or that's what linear means. And these are roughly linear relationships here. Vehicle maintenance, end of life, these are minor contributors. So these are really the two things. Just how much material do you need? How big is this vehicle? How much, that determines how much materials you need. That determines how much energy it takes to assemble this thing. So if we relate, say, the curb weight of a new vehicle to the emissions associated with its vehicle cycle, again, primarily its manufacturer, well, based on the GREET 2 model, these are results I've abstracted from the GREET 2 spreadsheet model. Well, our average new vehicle is just about 4,000 pounds for the last few years, and that corresponds to just about 9 metric tons of CO2. And that's true. So I have two curves here, and they basically are the same. I have a blue line and a green line, and that's conventional and hybrid vehicles. So they're virtually the same line. Pound for pound, hybrid vehicles have virtually the same emissions. And so that battery, even though it is in fact true that batteries do take a lot of energy to produce, and that energy can become very significant with battery electric vehicles that have very large battery packs. I'll talk about that in a separate video. It is not true that that outweighs, that is a significant contributor with just simple hybrid electric vehicles. They have a very small battery, comparatively speaking. And yes, a hybrid vehicle may be a little bit heavier than a non-hybrid vehicle in the same class, a few hundred pounds, but that's not a huge difference. So there's not a qualitative difference. And now this vehicle cycle is around, let's say, 10% of the life cycle emissions for a standard conventional vehicle. Sorry, this ICE means internal combustion engine vehicle, and maybe around 20% of the emissions for a hybrid electric vehicle. But that's not because it takes more energy to make the vehicle. It's just because over the life cycle, the hybrid generates less emissions from the tailpipe, from the fuel cycle. So it's just that the relative proportion of the vehicle cycle is larger for the hybrid. It's not that they're, in absolute terms, either taking much more energy for the vehicle cycle or certainly not overall. So that's what we can conclude there. And we can kind of say, just again, rule of thumb. A rule of thumb is it's around 2 to 2.5 kilograms of CO2 per pound of vehicle, if you want to do this multiplication yourself. And again, these hybrid and conventionals are virtually identical pound for pound. So if we just do these calculations again, our Hummer here, 6,600 pounds, it's around 15 metric tons of CO2, whereas our Prius is, a little over 6 metric tons of CO2. So almost a 2.5-fold difference just based on this. So obviously not a huge difference if we're using, Argonne National Lab numbers in not only the fuel use, but also the energy and emissions for the vehicle cycle as well. And if we just, this is Hummer versus Prius, this is not really a practical comparison for most people. I'm just using it because there's kind of that idea. It's just kind of an extreme example. But if we just talked about a typical car, so again, a typical car getting 22 miles per gallon, or typical vehicle, I should really say. Well, again, over 12,500 miles, we're talking, close to 600 gallons of gasoline, around 6 metric tons of CO2. Over the lifetime, around 80 metric tons of CO2. And over the vehicle cycle, as I just said, 9 metric tons CO2, about 90 metric tons CO2 equivalents over the life cycle of a typical car. Just a typical fleet car right now. Maybe, a little bit lower for a new vehicle, but not that much. For a Prius, let's say just the standard 52 mile per gallon version, assuming you really get that, well, over the life cycle, you're only using, you're using less than half the fuel, less than half the CO2 associated with the fuel cycle. And in fact, the Prius is even lighter than the average new vehicle. It's only around 3,000 pounds. And so that's around 7 metric tons of CO2 for the vehicle cycle. So less than half the life cycle impact from a Prius versus a typical car, or, about half the life cycle impact versus a typical new car. So you're saving not only compared to the Hummer, but compared to an average, standard vehicle, you're saving quite a bit of energy with the Prius or any other hybrid that gets that gets pretty good miles per gallon, anything in the neighborhood of 50 miles per gallon. Okay, so just final, just not to perseverate too much, but lifetime scores for the Hummer. If we add up all this, 17,000 and change gallons of fuel, vehicle cycle, 210 metric tons. Our Prius, well, this is just using the 2005 version, which gets a little bit worse, MPG, 45 metric tons CO2. And so our Hummer is in fact equal to more like 4.5, 4.6, 4.7, something like that pre-I. So no comparison, no comparison. I mean, well, there is a comparison, but it's not, they're in no way comparable. So summing up, we can sum up, we can summarize the impact of any vehicle really overall. Again, just according to the fuel cycle, vehicle cycle, and then the combined life cycle impact. And that's going to depend on the miles driven per year and the MPG per year. And if we just looked at the fuel cycle, say, and then we said, you know, you got some MPG here and some MB and some miles in thousands per year. This is how much CO2 you would emit over the course of that year. So if you got about 21 miles per gallon, 12,500 miles, you know, this is roughly typical, you know, just slightly underestimating. It's just that I'm going by threes here. So that's the one. This is an average. This is an average driver. You know, 6.6 tons of CO2 per year. You know, you can, and so what you can do is you can change your impact by going along either of these axes, in fact. So don't forget about miles. It's not just technology, it's behavior. It's how you use technology. So if you went up to 51 miles per gallon, okay, well, you go down by close to 2/3, 2.7. But you can also just reduce your miles driven. You get the same impact going here. Ideally, you can do both. You know, you can go, you know, here, you know, one metric ton of CO2 versus almost 7. Or you can, you know, or you can go the other way. You know, you can go here. You're getting, you know, you can go 20,000 miles a year in a truck that gets 12 miles per gallon, you know, using close to 20 tons of CO2. So, you know, this is a double-edged sword. You can go either way. And remember, there's this hyperbolic relationship. So your changes here, you know, in this kind of range are a lot more important than your changes here in terms of MPG. But your changes along miles driven, well, that's always impactful, you know, relatively speaking. And that's the fuel. However, we can also just, you know, simply incorporate weight, vehicle size, vehicle cycle. And as it turns out, for at least conventional vehicles, if you just plot the curb weight, and this is for the top 30 selling vehicles in 2014, so this is a few years, but it's the same relationship for now. You get a, you know, virtually all this variation in fuel consumption is explained by that vehicle weight. And then if you plotted this against MPG, well, this basically, this linear relationship converts into this hyperbolic relationship, and you see this here. But what you can do, well, if you know that MPG, you know, gives you, for a given MPG, you basically know what the weight of the car is going to be for a conventional vehicle. You can do the same thing for hybrid vehicles. Well, then if you know this MPG here, you know, here, well, then you can determine the weight. And then you can use our rule of thumb or our graph from before, and you can say, well, what was the vehicle cycle? And then what you can do from there, you say that, well, there are total emissions, and you just divide those into, say, an average vehicle lifetime of about 12, 13 years. And that gives you kind of your annualized emissions. So if we add in those annualized vehicle cycle emissions based on the inferred weight from the MPG of the vehicle, we can get a new table, and we can say, again, you know, we have the same relationships, but once we include all that, a typical driver is generating over 7 metric tons of CO2. And then you have all the same, you know, qualitative changes as you move around here. It's just saying that you add a little bit for that vehicle cycle emissions. But overall, fuel cycle, totally dominant. And of the fuel cycle, it's the tailpipe component that's dominant. And so, you know, hybrids, conventional vehicles, we can compare them on the basis of MPG quite nicely. We don't have to make an adjustment at all for the different classes. This is not necessarily true for electric vehicles, but for hybrids, this is true. And so what we can say is that the impacts across the vehicle life cycle, there are impacts across the vehicle life cycle, but as I just said, these direct tailpipe emissions are dominant. We can compare different hybrids, conventional vehicles, just using MPG. And it's important to keep in mind, again, that increasing this MPG at the low end is far more impactful at the high end, going from a truck, SUV, thing like that, to just, you know, any hybrid that's in the neighborhood 40, 50 miles per gallon is, you know, it's so much more difference there at the low end. Our typical driver is going to use, you know, close to 600 gallons of gasoline per year, translating into about 6 metric tons of CO2 per year. you add in that vehicle cycle, you're getting closer or even greater than 7 metric tons of CO2 per year, which is roughly the average carbon impact from everything for the average global citizen. So Priuses or similar hybrids, again, it's not just Prii, but I'm just focusing on that because that's what I have and that's what I can show you how it works directly. Most directly, they're getting half the fuel, half the CO2 over the life cycle compared to other typical conventional vehicles. Don't forget about your miles driven. That's just as an effective or even more effective way that synergizes with getting good efficiency. And just let's put this Hummer Prius bed to myth forever. The Hummer H2, in terms of its energy and emissions and fuel uses, is basically the same as almost 5 Prii. So that's it for this lecture. Next time, let's talk about how this hybrid drivetrain actually works. How does it give you this good MPG? We'll talk about that, and then once we know that, we can then proceed to win the Prius video game. So that's that. That's everything. Thanks for watching.